Hello everyone. This is gonna be the recitation class that we were supposed to have on Friday, right? This is my second attempt actually trying to record. I managed to. I continued speaking like for a while, and then I discovered the recording froze for some reason. I'm using that Xbox tool that's available for Windows. I guess it's popular with game streamers. Okay, so it's a free tool and it seems to be working just fine. So just have to be careful and make sure that I'm always recording. Okay. All right. So remember when we talked about transmission lines, right? This was one application of Gaussian surfaces. We could use a Gaussian surface to easily calculate the electric field around that line. So a transmission line would be like if you have the ground, right? So you have the ground, and then the transmission line is going to be above the ground a certain distance. So the question is, what would be the field at the ground due to the transmission line, right? And the simplification here that is imparted due to Gauss's theory is the following, right? We could imagine a Gaussian surface that looks like a cylinder around the transmission line. Imagine an infinite transmission line, right? And this Gaussian surface has a length of L, right? And there are three surfaces here, really. It's a closed surface, but it's composed of three different surfaces. So there's the surface of the cylinder, S1, and then there are the caps on the cylinder, S2 and S3. Okay, we said due to symmetry, we would expect the electric field to be a function of R, which is the distance from the transmission line, and then the field will always be emanating away from the transmission line. Okay, so that tells us also that, remember Gauss's law. Let's write down Gauss's law again. So it's a closed surface integral over the whole surface of E ds equals Q enclosed over epsilon naught. Okay. For the S now is the whole surface we're integrating over is going to be S1 plus S2 plus S3. But notice that the field in S2 is always going to be embedded within that surface, meaning that the vector representing that surface, which is perpendicular to the surface, is always going to be perpendicular to E. So the dot product here is always going to be 0 on S3 and S2. Okay, the only part of the integral that has any value is going to be the integral over S1, and that will simply be E. The magnitude E is just the magnitude of E, right? And then the area of that cylinder, which is going to be 2 pi r L. Okay. Assume here that the transmission line has a line charge density of rho L, right? So the total enclosed charge is going to be rho L times L over epsilon naught, right? So we can divide L here out, and then we end up with the magnitude of E equals rho L over 2 pi epsilon naught R. Okay, so this is the electric field at distance R away from the transmission line. Notice that we lost the vectorial information, right? Because we're doing a dot product, of course, so we're going to lose the vectorial information, but we can easily put it back in. This is a feature of applying Gauss's law, and it happens due to the symmetry. Things happen that way because of the symmetry of the Gaussian surface, right? So I can easily, in cylindrical coordinates, put back that vectorial representation. So I can say as a vector E equals rho L over 2 pi epsilon naught R hat Newton per column. And when we studied the potential energy, we discovered we can also write the electric field intensity in units of volt per meter. Okay, so now the problem we want to solve, so we figure out the electric field, we did that already. We figured out the electric field for a single transmission line. What if we are solving a problem where we have two parallel transmission lines, right? We can still use the result we got from Gauss's law. I mean, it's the same, but now we can apply superposition. Superposition still applies, right? We just have to be careful with the coordinate system. You know, here in this example, I've placed the transmission line at the center of the coordinate system, meaning that the distances in space away from the transmission line are r. So probably here the line is, no, actually here the line is parallel to the z-axis or superimposed on the z-axis of the cylindrical coordinate system, right? But when I have two lines, you know, I just have to be careful with the coordinate system math because only one of them can be the z-axis. Okay, so I'll show you how to do that right now. All right, so okay, so we have two transmission lines. One transmission line has a charge density of rho L, right? Coulomb per meter, and then the other line has charge density of minus rho L, Coulomb per meter. Okay, so so we want to figure out the right coordinate system to solve this problem. We want to find the field due to those two lines. Okay, it will simplify things if we orient our coordinate system for this problem in this manner. So imagine the two transmission lines crossing a surface, right, at 2 points, right? So imagine this surface. Let's select our coordinate system. It's a matter of choice what coordinate system we select here, right? So let's select our coordinate system such that this surface is the xy plane. So I can draw it this way. So I can draw the x and y plane, and the z plane is going out. So the z plane is going out of the board, right? So we don't see it here. And then the two lines are crossing the xy plane this way, the two transmission lines. Okay, so we see them as dots, right? But they are crossing the xy plane. And the problem states that the distance between the two transmission lines is going to be 2 meters. So this is A equals 2 meters. And then the distance from the ground. So assume y is the, well, clearly here we are assuming that y is the vertical direction, right? And x is parallel to the ground. So the distance from the ground to the top transition line is d, and the distance between both lines is a. So how do we find the electric field of this problem? Well, we know what it is for a certain line, right? So it's going to depend on the distance, right? So there are two distances here. So there is R2, and then there is R1. So there's a distance from the bottom transmission line and a distance from the top transmission line. And we know what the electric field is for a single. Let's say, let me draw a transmission line here. Right, at any elevation, let's say elevation y1, right? So we know we can find the field an r distance, r1 distance away, right? In terms of Cartesian coordinates, r1 squared equals x squared plus y minus y1 squared. This is from the equation of the circle, right? So that means that r1 can be written as x squared plus y minus y1 squared square root. Right, so this is the distance at any point in space from the first transmission line. Likewise, the distance from the second transmission line is going to be x squared plus y minus y2 squared, where y2 is going to now be the elevation of the second transmission line. Okay, so this allows me to write the field at any point in space, right? At any point in space, I assume that there are two components to the field. There is the field coming from the positive transmission line, the one with the density of rho L, and there's a field coming, so this is this field, and then I sum it up with the field coming from the negative transmission line, the one with the charge density minus rho L. Right, let's call this E minus. Right? So using all this, I can write E plus equals R1, the unit vector in the direction of R1, which we will rewrite in Cartesian coordinates soon. But if you remember, yeah, we derived this, right? So it's rho L in this case. So it's going to be rho L over 2 pi epsilon naught R, but instead of R, I'm going to put in R1 here, which is going to be x squared plus y minus y1 squared. Right? And then E minus, the field due to the negatively charged transmission line is going to be minus R2 rho L over 2 pi epsilon naught x squared plus y minus y2 squared. Okay, so let me redraw this. Right, so we have the y-axis, we have the x-axis, we have two transmission lines, right? And then we have a field at the point, right? So at that point, I have E plus but that E plus is going to have two components, right? So it's going to have a component along the x-axis, right? And a component along the y-axis, and the angle here, let's call it theta 1. Right? And then E minus is going to be so this is coming from here, right? From the positively charged transmission line. From the negatively charged transmission line, there's going to be field pointing towards it, right? E minus. Fields always extend or emanate from positive charges and go towards negative charges or point towards negative charges, right? And again, this will have an angle theta 2. And again, we can compose this into two components. Component in the x-axis direction and component in the y-axis direction. So we can really rewrite E plus vector as x hat, the magnitude of E plus cosine theta 1 plus y hat, magnitude of E plus sine theta 1, and then we could write E negative vector as minus x hat cosine of theta 2 minus y hat. Oh, of course, I forgot the E minus here, the magnitude of E minus, the magnitude of E minus sine of theta 2. Right? So I know how to write cosine theta 1 and cosine theta 2, right? In terms of Cartesian coordinates. Cosine theta 1 is just going to be x over r1, right? It's going to be x over x squared plus y minus y1 squared. Okay, let me make the figure a bit clearer, more clear. So let me erase this. Right, to show you how do we evaluate the cosines and the sines. Right, so this is the x-axis. We're interested in finding the total field at a certain point in space, right? So this certain point in space will be at, xy, right? And then actually let me draw it somewhere here. Okay, so this will be some point xy. Okay, so there's going to be like a distance r1, and then there's going to be E plus field, right? And then there's going to be theta 1, right? Notice that theta 1 here will be equal to theta 1 here. This is from basic geometry, right? And theta 1, so we have this triangle here, right? So theta 1, cosine theta 1 is going to clearly be x, this is x, of course, over r1, right? It's going to be x over r1. And same deal with, so that's how I calculated cosine theta 1 to be x over r1. What about sine theta 1? What is that equal to? Well, sine theta 1 is going to be this distance here, right? What is this distance? This distance is just, right, so this line here is at y1 coordinate and y2 coordinate. The y-axis represents the distance from the ground, right? So this distance clearly is going to, if this point in space is at coordinate xy, this distance is going to be y minus y1, right? So sine theta 1 is going to be y minus y1 over r1. It's going to be y minus y1 over square root of x squared plus y minus y1 squared. Okay, that's where that comes from. So now what remains is finding cosine theta 2 and sine theta 2. Right, so we already know the magnitudes, E plus and E minus. To write the vectorial equation for E plus and E minus, we need to find the cosines and the sines, right? So cosine theta 2, all right, cosine theta 2, I can find the same way. Let me just copy this so that I can state things clearly. So copy is this, and then paste. Okay. Okay, let's see. All right. So same thing. This is still point xy, right? But now I want to look at the field coming. I want to look at the E minus field. Right. So this is still point xy, right? So the E minus field is gonna be this field, right? And then there's going to be an angle theta 2. So you've shown that somewhere here. Right? This is R2, right? And clearly cosine theta 2 is going to be x over R2, and sine theta 2 is going to be so this is to be this distance. This distance is y minus y2, right? So cosine theta 2 is going to be y minus y2 over R2, and I can write this as x over square root x squared plus y minus y1 squared, and I can write this as y minus y2 over R2, which is x squared. Oh, sorry, R2 is y minus y2 squared. So this is going to be x squared plus y minus y2 squared, right? So we can take those four expressions and plug them in here to get the total electric field. The total electric field is going to be the sum of E plus and E minus. So the total electric field due to those two lines, located within the coordinate system in this manner, is going to have an x component, right? So it's going to have right, an x hat component and a y hat component. First off, the magnitude so it's going to be this part for the x hat component plus this part. The magnitude of E plus and E minus, we already found that, right? So the magnitude is here, right? So this is the magnitude of E plus, and this is the magnitude of E minus. So we can take out the common factors, which is rho L over 2 pi epsilon naught. So this is going to be, this is the x hat component, rho L, rho L over 2 pi epsilon naught, right? And then there is this square root times cosine theta 1, which is x over square root. So square root cancels with square root, and I end up with x over x squared plus y minus y1 squared, right? Minus cosine theta 2, which is this term here, which is x over the square root. Again, the square root cancels, right? So it becomes x over x squared plus y minus y2 squared. I can take the x out, of course. So I end up with this term. So this is the x hat component, then y hat component is the same thing. Right, so I have the magnitude of E plus and E minus. The common terms are rho L over 2 pi epsilon naught, of course, so I can take those out. Rho L over 2 pi epsilon naught. And then, so I took out the common terms, and then what remains is E plus sine theta minus E minus sine theta, the rest of the terms. So sine theta 1 is this term multiplied by the square root cancels, and then same thing, right, for the other term. So I end up with y minus y1 over x squared plus y minus y1 squared minus y minus y2 over x squared plus y minus y2 squared. Newton per coulomb. And this is the total electric field due to two transmission lines. Right. So if we have two transmission lines, the first is at distance y1, the second is at distance y2. I think it's the opposite, actually. Yeah, it's the opposite. The first one is y2, the second one is y1, and this has charge density rho L, this has charge density minus rho L, right? And then we have, this is the y-axis, this is the x-axis, right? We can find the electric field at any point in space using this formula. Okay. Let's say you wanted to find it at the ground. At the ground, right under the transmission lines. Let's say you go to some transmission lines and you stand right underneath them. So what's the coordinates of this point? It's 0, 0, right? So x is 0, y is 0. In that case, the field at 0, 0 is going to just be put in 0 for x and 0 for y. So the x component cancels out, x hat component cancels out. I only end up with a y hat component, right, times rho L over 2 pi epsilon naught times what? Times y is 0 and x is 0, so I end up with minus y over y1 over y1 squared minus y2 plus y2 over y2 squared. So I end up with y hat rho L over 2 pi epsilon naught 1 over y2 minus 1 over y1. This is the electric field right underneath the two transmission lines. Alright, and this is the end of this calculation. Okay. Okay, so let's see. This is pi here. Looks like tau. Alright, so the second example I want to do, problem I want to solve is relates to applying Gauss's law in reverse. So up to this point we were using Gauss's law to if we have like some charge distribution, we get electric field intensity. But what if we have an electric field intensity in a space defined, we know what the electric field intensity is. Can we use Gauss's law to find the charge distribution, that generates, let's say this is plus Q minus Q, whatever, yeah? Can we use Gauss's law to figure out the charge distribution from the electric field? Yes, we do, and example 4.5 is shows you one way of doing that over. Right? So let's see, what does the example say? So it's an application. Electric field intensity and charge density in and around a thundercloud. And like everything in physics, this is simplified, so the assumption is that it's a spherical cloud. It's a cloud that looks like a sphere. So it's a spherical cloud, kind of similar to the joke about, how do physicists, solve a problem. Let's say there's some problem that has a cow in it. So the joke goes that they would say like and assume a spherical cow. So in a similar manner here, we would assume a spherical cloud. So this cloud has a bunch of water droplets, has a bunch of charges in it, charge distribution, right? And let's assume it doesn't have to be a uniform charge distribution. It could be a non-uniform charge distribution. Perhaps as we go more towards the center of the cloud, we will have more charge, maybe we'll have less charge density. We don't know. But what we do know is that the electric field within the cloud and just at the border of the cloud, it looks like this. The electric field is going to be r hat r squared, right? So here the assumption, of course, is that we are doing the assumption here is that we are doing spherical coordinates, right? So we are at distance r, and the center of the cloud is the origin of the spherical coordinate system, right? So we know that this is what the field looks like, and this is for r less than or equal r naught, where r naught is the radius of the cloud. So this is the radius of the cloud, and r naught is 1 meter. Okay, so the problem asks for two things to solve for. We want to find the total charge within the cloud, and then we want to find the charge density. Okay, so the total charge comes from Gauss's law. So remember, if we integrate over the surface, closed surface, and that surface is the border of the cloud of E dot ds, that equals Q enclosed over epsilon naught. So this is the total charge, Q enclosed. So if we assume that the Gaussian surface is the boundary of the cloud, then that we can use that to give us Q total. So in that case, E at the boundary is going to be what? It's going to be has a magnitude of r squared, right? R naught squared in this case. So you see here E equals r naught squared. So that's the magnitude of E. And the surface we're integrating over is a sphere, right? So the sphere has a surface area of 4 pi r naught squared, right? That equals Q over epsilon naught. So that tells me that Q total equals 4 pi epsilon naught r naught to the power 4. Since r naught is 1 meter, this is going to just be 4 pi epsilon naught, but I'll leave it this way, right? To make it more general. What if the cloud had a radius that's other than 1 meter? Maybe the cloud had a radius of 2 meters. Right? So we calculated the total charge using Gauss's law and inverse Gauss's law. Right? Then part B, what is the charge density of the cloud, of the charge in the cloud, right? So from symmetry, we can see that because if we rotate the problem, if we look at the problem from a different angle, the problem doesn't change really. It's still a spherical object, right? So if we would guess, and we would guess correctly, that the charge density is only a function of the radius, right? The distance from the origin. It's not a function of the angle, right? It cannot be, because the electric field itself is not a function of the angle. It's only a function of the radius, right? So the assumption here is that, well, which is true, is that the charge density, the volume charge density, is a function of r. Okay, there are two ways now to calculate the volume charge density. We could just integrate, so we know what the total charge is, so we can just integrate over the volume, right? And we should get Q total, which we know what it should be, right? And that should allow us to solve for rho v, right? That's like a more complicated approach. The other approach is to just use the divergence, right? We know that the divergence, this is, remember, the first postulate of electrostatics, right? So this is much more straightforward thing to do. Let's start with methods. I'll call this method 1, and this is method 2. Let's start with method 1. Okay, so the assumption is that Right, so this is over the whole volume, which is the volume of the sphere, and rho v is a function of r, right, dv. So I need to separate this. I'm doing cylindrical, not cylindrical, sorry, spherical coordinates. So this is going to be rho vr, and then the volume element is going to be r squared sine theta dr d theta d phi. Right, we know that already. And then so let me, I wanna, and now I don't know what function of r rho v is, right? But I know it's not a function of theta or phi, so we still can integrate over theta and phi. So let me rearrange those actually. Let me do d phi first, and then d theta, and then dr, because I follow the convention of matching the limits with the differential elements. So I start with phi. Phi goes from 0 to 2 pi. Theta goes from 0 to pi. This covers the whole sphere. And then r goes from 0 to r naught. R naught is the radius of the sphere. Okay. Right. So this. Okay, so theta part is easy. Theta part is, there's no theta, sorry, phi part is easy, so there's no phi here. So I just integrate from 0 to 2 pi, I just get a constant 2 pi. And then go from 0 to r2, 0 to pi, right? Rho v r squared, sine theta, d theta, dr. Right? At this point, I just need to integrate. So notice this thing is not a function of this term is not a function of theta. I can take it out. So I have rho v r squared, and then I have to just integrate. This is dr. I just need to integrate sine theta with respect to theta, which is what? Which is minus cosine theta, right? Differentiate cosine theta, you end up with minus sine. Minus cancels with minus. So this goes from 0 to pi, right? Cosine pi is minus 1, so this becomes 1. Minus 1 times minus 1 is 1, and then minus cosine 0 is 1. Did I do something wrong here? No, this should be right, because I'm integrating. Yeah, I'm integrating from 0 to pi. Cosine pi, I said, is minus 1. This becomes 1, and then minus. Okay, minus cosine 0. Cosine 0 is 1, so minus 1, this becomes plus 1. Okay, it doesn't turn to 0. I was confused for a bit. So this is 2. Okay, this turns out to be 2. So we end up with 4 pi 0 to r naught rho v r squared, right, dr. So this is the volume integral. Now remember, this whole thing needs to be equal to, using Gauss's law, q total, right? That's what it should be equal to, but q total is also equal to, so this should be equal to q total, but q total is also equal to, we found in part A, q total is also equal to 4 pi epsilon naught r naught to the power 4. 4 pi epsilon naught r naught to the power 4. So notice here, 4 pi is the same as 4 pi, right? So that part is the same. Now we want to make sure what could rho v be, such that when we integrate it, we end up with rho naught to the power 4. Where what if we integrate 0 to rho naught? What if we integrate epsilon naught r to the power 3 dr? Right? That will give me. I'm assuming that rho v in this case is epsilon naught r squared, right? So I end up with, sorry, epsilon naught r. You know, rho v is epsilon naught r, so I end up with epsilon naught r cubed. If I do that, I end up with r to the power 4 over 4 epsilon naught, right? But let me put an extra 4 here, so I end up with this term. Okay, so notice if I assume that rho v equals epsilon naught r, when I integrate it, I get this term instead of the integral that equals, of course, r naught here, that equals this part here. Right? So the way to guarantee that the right-hand side equals the left-hand side is to assume that rho v equals epsilon naught r. Right? So when I do that, when I plug that here, I end up with 4 pi epsilon naught 0 to r cubed dr equals 4 pi epsilon naught r naught 4, right? And this right hand side is equal to this left hand side, right? I can see that clearly. So this is going to be 4 epsilon naught r, right? That's what we said, right? So okay, rho v is 4 epsilon naught r. So yeah, I end up with r4, which gives me 4. When I differentiate it, gives me 4r to the power 3, and this is from 0 to r naught, right? This equals 4 pi epsilon naught r naught to the power 4 equals 4 pi epsilon naught r naught to the power 4. So there was a bit of guessing here. So I looked at the right hand side and I thought to myself, hey, what can I plug in for rho v? What function can I plug in for rho v such that when I integrate it, I make the right hand side and left hand side equal? And that turned out to be rho v as a function of r equals 4 epsilon naught r, right? Coulomb per meter cubed. So those are the units. Okay, let's do now the second method, method 2, which is just simply using the divergence. It's very straightforward. So the divergence of E, postulate 1, right, equals rho v over epsilon naught. So rho v is going to be epsilon naught divergence of E. Okay. E in this case, where is E? This is E. Right, so we can write the divergence formula in spherical coordinates, but because E in this case is only a function of, has only an r hat component, and even that r hat component is not a function of theta or phi, that tells me that the components of the divergence that are coming from theta dependency or phi dependency will be 0. So I could just write divergence E equals 1 over r squared delta r squared ER. So this is one part. This is the r component of E, right? Over delta r. And then there are two other terms, right? But we can ignore those terms because they are 0, right? You will find that there is no E phi and there is no E theta. So those terms will be 0. And the divergence is going to simplify to just this term. This is something we can calculate, right? So this is 1 over r squared delta over delta r. Oh, let me take this out. Delta over delta r. So r squared, what's the radial component of E? The radial component of E is this r squared, right? So it's going to be just r squared. So this is going to be r squared, right? So it's going to be 1 over r squared d r4 over delta r. This is going to be 1 over r squared times 4 r cubed. So we end up with 4r. Okay, So I plug this back into here, and I end up with rho V equals 4 epsilon naught R, which is the same result that we got previously, Coulomb over meter cubed. Okay, so we're done with this problem. Okay, so now I want to do example 4.6, right, which states that we want to, let's say we have two very large plates of material, right, surfaces essentially. So the assumption here is that those two plates are almost infinite, or infinite pretty much, right? The idea is that we want to generate a field in between the plates, certain field E naught, right? And the distance between the plates is D, right? So we want to generate a field between the plates of a certain intensity. So what kind of charge density do we need on those two surfaces to generate that field? The idea is that the field is only contained between the plates. There is no field outside the plates. So outside the plates, the field is zero. So only sandwiched between the plates do we have a field intensity. Okay, so we can apply reverse Gauss's law here. So if I go, if I go to the upper surface, let's say, so I'm taking the upper surface, and then I do my Gaussian surface. My Gaussian surface might look like this, right? So it extends so it starts above the surface, and then it extends to below the surface. So above the surface is in green, red, and below the surface is in green, right? And it extends below the surface. Let me make it dotted so that, right? And we said there is no field. I mean, of course, there is surface S1 here, surface S2, and then the S3. We said the green part of the Gaussian surface is going to be below this sheet, right? We said the field will only exist here on the lower surface. The field, of course, by design, the field is going to be perpendicular to the sides here, right? So this is E naught. So using Gauss's law, the surface over the total S is going to be E naught ds, right, equals rho S. Let's assume that S1 equals S3 equals S, right? The upper surface and the lower surface are equal. The upper caps and lower caps of this Gaussian surface are equal, right? So it's going to be rho S, right? So you end up with E naught, the magnitude of E, S, right? Oh, of course, Gauss's law says we need to have an epsilon naught here. So E naught S, E naught is equal, right? And the surface, the lower cap of this Gaussian surface has a surface area of S. So this equals rho SS over epsilon naught. So this tells me that the charge density that gives me a certain field intensity E naught is going to be E naught epsilon naught. Right? Let's repeat this for the lower sheet. So if I take now the lower sheet, which is this sheet. Okay. Right. So the same deal. Okay, so I have the surface, part of the surface, Gaussian surface, in the middle between the two sheets, and then the part that's under this lower sheet. Okay, and there's no field in the red part, so there's no field here. E naught is 0. the field only exists here, and the field should be in this direction, right? So in this case, right, it has to be equal to the field that we calculated here, right? So in that case, S E naught ds equals rho SS over epsilon naught. So this equals minus E naught, right? Because the field now has an opposite direction. S rho SS over epsilon naught. So E naught should be minus rho S. S cancels with S. Right? Over epsilon naught. So rho S equals minus epsilon naught E naught. Okay. So this is an example of a capacitor, right? Because now to generate this uniform charge density, to generate this uniform electric field intensity between those two very large sheets, we need to have a charge density on the upper sheet that's positive, right? That's equal to epsilon naught E naught, where E naught is the desired electric field intensity. And then at the same time, there should be a matching charge density in the lower sheet that's equal to the upper sheet but negative. And we arrived at those results using the inverse of Gauss's law. Okay, so yeah, so I'm gonna so I posted, I was playing with this thing, so I kind of like just recorded a number of videos, and then in post I'm gonna trim them and combine them together, and we'll see how it works, and then I'm gonna post them online. So what I'm gonna do, the plan is to post them in a discussion thread, those video lectures, and then I'll open the thread for a day or two so that I can gather questions. So if anyone watches the videos and has questions, there's a window of opportunity to pin those questions down in the discussion thread so that I can address those questions in the next lecture. When the next lecture is posted, I'm going to close the discussion thread tied to this video and then open a new discussion thread, right? So that I don't want anyone to post something like that in last week's discussion thread and then I miss it or something like that. All right, thank you guys, and yeah, I think I'm learning how to do this slowly. Hopefully things will go smoother in the next lecture. Thank you.